maybe we can get started. So again, Vincent very gracefully accepted to do his talk now because Jeff's having internet problems. So hopefully if Jeff's internet is back, we're gonna have his talk at 2 p.m. So it's a pleasure to have Vincent from UC Berkeley. He's gonna talk about preparing the SYK TFD on a quantum computer. Thank you, Vincent.
All right. Yeah, thanks for the introduction. I'll be telling you about preparing the SYK Thermofield double on a quantum computer. This is based on work I put on the archive towards the end of last year. Yeah, I just wanted to, again, thank the organizers for giving me the opportunity to speak. I think that this collaboration is really one of the best places to be presenting this work, so I'm excited to share with you all. Now, before I dive in, I wanted to provide a brief motivation of like how this work even came about. And I think that a lot of these goals will really resonate with you also. I wanted to share them. The first is, now that we're in an age of quantum supremacy, the pressing question, right, is like, how can we use these available oncoming devices to learn new things about physics? From the quantum gravity perspective, theory has kind of gone a bit astray from experiment. And, optimistically, I want to ask, is there possible ways we can experimentally confirm ideas from ADS-CFT? This is very much in the same spirit as the quantum gravity in the lab program. More generally, I'm also pretty excited by like the sorts of tests that quantum computers are uniquely poised to do. Apart from the handful of known quantum algorithms, I think that we're really on the cusp of research getting to the point where we know more about what these tasks are. So I wanted to just preface this by saying that, in the short amount of time that I have, I'm really going to be talking and focusing on one idea, and that's of variational quantum computing. So while I think that the physics aspects are very interesting, again, in this time-constrained arena, I wanted to illuminate this particular aspect, partially because I think that it would be relevant for everyone in the audience, and also because I think it might be a little bit less familiar. So I want to do my best to shed some light on this area. Okay. So a brief roadmap of where we're going today. I'm going to start with just a quick background slide on the physics. This will just be establish us on the same page. And then after that, I'll lead us through a series of questions. What is variational computing? How do we actually take our variational ansatz and tune it to do the thing we want to do? In this case, preparing the TFD. And then the last thing I'll kind of ask, right, is can a quantum device today get the job done? So as promised, a brief background slide. I think many of these, if you're a regular at these GeoFlow talks, then this will probably be yet another refresher. So the first thing I want to review is Thermofield double states, and these are quite generic. So given a Hamiltonian that defines your quantum system, the Thermofield double is a special state that's defined on two copies of the system. So the particular form of the state, it's this superposition over entangled energy eigenstates on both sides, weighted by these Boltzmann coefficients. One way you might think about this is as a particular purification of a thermal state on one side. So, we said that it's defined on two copies of the system. If you were to trace out the left side, you'll be left with a thermal state on the right side, and vice versa. In the context of ADS-CFT, this is dual to an eternal two-sided black hole. So that's one reason why you might be interested in studying this state. But the TFD state has a lot of interests beyond that. I think probably we could crowdsource many other reasons why you might find the TFD state particularly interesting. I'll just name a few applications. So it's usually taken as the starting point for scrambling, teleportation, and traversable wormhole protocols. So these are just a few of the things which you might be interested in studying and looking at this state. Now the SYK model, I don't want to beat a dead horse, but just so we're on the same page, right? It's n-Majorana fermions with all-to-all connectivity. There are many variants floating around. I'm going to pick the one with 4-body interactions. Again, the couplings here are chosen to be random variables. And those random variables are distributed normally with variance set by a parameter j. So You can think about J as the overall coupling strength of the system. A quick note on why it's interesting. We've already heard some review of this today, but in a certain low energy limit, it's dual to a theory of 2D quantum gravity. For the purposes of this talk, it's going to be some concrete quantum mechanical system once we've flipped our coins and sampled these coupling strengths. So once we've fixed those, it's just some concrete quantum mechanical system that we can deal with. So the goal of today's talk is going to be to prepare the Thermofield double state for a fixed instance of this SYK Hamiltonian. So this is the problem we're going to tackle, and I'm going to switch gears now to talk about variational quantum computing. And to illustrate the ideas, we're gonna look at a single qubit. Single qubit is nice and clean. You can visualize everything on the Bloch sphere, so that's going to be kind of what we'll refer back to. So the starting point is we're going to prepare our qubit in the 0 state. We're going to then apply some rotation gate about the x-axis that's parameterized by this angle theta. Now, what's important about this is, theta could be an experiment. It could be like the duration of some pulse, or it could be the amplitude of some pulse. But the main idea is that it has to be something that you can tune, or you can dial in and adjust. So as a result of putting this variational gate, applying this variational gate to our fixed input state, we also end up with a variational state psi. Our output state psi also depends on these gate parameters. Okay, on the right, I have a more visual representation of this. So on the Bloch sphere, you can think about this qubit in the 0 state as living on the North Pole. I've abstracted away the quantum circuit into this unitary that depends on theta. And for this particular class of states psi, you can actually visualize it as just a circle living on the Bloch sphere. So this class of states psi of theta is somewhere on this circle on the Bloch sphere. Okay, and then theta conveniently describes this angle from the North Pole. Okay, so that's our variational setup. Now let's suppose that the task we want to do is we want to minimize the expectation value of z in this class of states. And I want to just give a brief moment to the audience to help me to think about this question, right? Like, what is the best angle I should choose for my state psi if I want to minimize the z expectation value? Okay, and if you know, you can either unmute yourself or help me out in the chat, I suppose. Okay, where again, we can, in this case, we have the tool of our friend, the Bloch sphere. Okay, so in this Bloch sphere, right, the z expectation value is just given by like the height on the Bloch sphere. So if we want to minimize the z expectation value, what we really want is to end up at this south pole. So the best angle we would pick would be pi. Now, what's more interesting than the answer here is like how we know this more generally. Whoops. So, right, the question is like how you know this, and let me just outline how people solve this problem in general. The first is you get lucky. There's some analytical expression, and then you find your minima that way. That's usually quite rare. The second way that's more common is you say, I'm going to plug in my class of states psi into the computer, and I'll say, look over all these different states and then give me back the state that does the best. And the aspects about this that I want to highlight are that it's exact, right? In the sense that you're kind of guaranteed to get the best answer within your class of states. But I should emphasize that it's extremely, terribly expensive. And it's really expensive in two ways. The first is that, generally, if you want to do this for a quantum circuit, the space that you need to even put this in your computer grows exponentially, right? And then the second aspect, which becomes really expensive, is the time. So if your circuit has more than one parameter, then searching for the best set of angles, at least in the naive way, also grows exponentially because you have a combinatorics problem. So very quickly, this second method is, if you try to put this on your computer, you're going to run out of both space and time. Okay, so the third way that I'll advocate for going forward is minimizing via gradient descent. In contrast with the previous method, it's a greedy algorithm in the sense that you're not always guaranteed to get the best answer. But on the other hand, it's going to be dirt cheap. So I'll say a little bit more about how we actually get these gradients in a moment. Okay. Now, at this point, the biggest question that I get is why? Like, why choose to do variational computing and why minimize with gradient descent? And I'll offer 3 reasons. So the first is that circuit design is like incredibly difficult, right? And as a testament to this, just think about how many exact quantum algorithms you can name. If that number is more than the number of fingers you have, then please email me because I would love to learn more from you. The second thing that the second reason that I want to do this is I want to avoid what was recently coined as cheating, in quotes. So, if you're at the point where you can plug in your class of states into the computer and ask it for the best angles, like you kind of don't need the quantum computer, right? Like the whole point of these bigger and better quantum devices is that they're going to teach us something new that you couldn't already compute with classical computers.
I have a question.
Oh, sure.
How do you actually do your gradient descent on a quantum computer? Like, how do you calculate the gradient? Because for me, because this already has a very simple analytical expression, so it's kind of hard to really see that it's an advantage of gradient descent.
Oh, sure. Yeah, good. So good. So exactly, this is a toy example where the gradient descent would be overkill. I'll say on the next slide how we actually calculate these more generally, but it's also going to work for larger system sizes. Okay. So yeah, the third reason I'll give in favor of doing gradient descent is an empirical one, and it's basically the observation that gradient descent is unreasonably good. It's way better than it has any right to be. And if you want a testament of how strong it is, just think about how much time you've spent on social media or YouTube. Like all of those algorithms are powered by gradient descent. So one quote that I think summarizes this quite well is that gradient descent is a better programmer than you. Okay, and this was echoed by Michael Nielsen, who, if you don't recognize by name, perhaps this picture might jog your memory, right? He's literally the guy that wrote the book on quantum computing. Okay, so yeah, at this point, I should tell you about how we actually take these circuit gradients. And there's this nice piece of machinery called the parameter shift rule. So again, I'm gonna use this toy qubit example, but hopefully it'll be clear how this generalizes in a second. So let me say what the statement is. And it's the statement that the derivative of an expectation value with respect to this gate parameter is actually given by the difference of 2 other expectation values. Now, you might think that's kind of obvious, right? Like, as physicists, one of the first tools we learn is Taylor expand. If you want to figure out the derivative, just take a small step to your left and a small step to your right and ask which way you do better. If we were to apply that to our toy problem here, what it would say is like at a particular angle theta, let's look nearby and see whether we do better by going to the left or to the right. In the numerics literature, this is often referred to as the finite difference method. But there's a real problem here for near-term machines. And that is that you don't want to take epsilon small for a noisy quantum device. Okay, so in contrast, what this parameter shift rule says is that if you want to evaluate the gradient at this point theta, you actually look macroscopically far away and compare the expectation values there. Okay, so The final thing that I'll mention about this gradient procedure, oh, sorry. Let me just reset the, oh, that's not, I'm gonna just resize this. Okay, so there's something I should point out about this rule, which is quite magical. So the first is like, it's not clear that you would be able to take the gradient of a quantum circuit. So that's kind of cool on its own. But the second aspect of this that is really quite remarkable is that if you can build the circuit, which even computes the expectation value that you're interested in, it turns out that that same circuit is the thing that calculates the gradient. So what you do is you basically run the same circuit, but with slightly different parameter values. Okay, so again, if you can build the circuit to measure the thing you're interested in, then you already have the hardware to calculate its gradients.
Another question about this theta. So here, from your expression, it looks like theta is just a scalar. So in general, does this hold if your theta is a vector?
Yeah, good. So if you have multiple angles, then this would just give you the partial derivatives. So you would just do it entry-wise, or like, yeah, you could, yeah, you would apply this for every entry in your theta element-wise. So
sorry, what decided that you choose the theta plus and theta minus to be at these opposite points? Like if it's more general, multiple parameters in a higher dimensional Hilbert space, do you just choose theta plus, theta minus to be some finite distance to theta, or is it like extreme?
Yeah, good. So it depends on the eigenvalues of the generator. So in this case, the generator of our matrix was the poly X matrix. And so these differences of pi over 2 from the original point basically come out from the eigenvalues of that matrix. So if you have a different generator, then the distance at which you would shift the angles depends on those eigenvalues. But let me just say again that, so let's suppose you had n gate parameters, then the number of expectation values you would need goes as 2 times n. So you need to do this for every different, like for all the parameters in your gate, you would do this individually. Okay. And then the final note that I want to make about this is that if you instead wanted to minimize the sum of, say, z and x, you can in fact apply the same machinery. And the reason you can do that is because both expectation values and the derivative operator are linear. So if, for example, you had a sum of polystrings, you could also apply this, this gradient rule to minimize that. Okay, so I gave a version of this talk to members of the SYK group. They also found this idea of like quantum circuit learning to be rather intriguing. So they actually implemented this toy 1 qubit problem on their hardware. So starting from some initial guess for theta, they were able to sweep out and indeed find the state at the bottom. Again, this is a toy 1-dimensional problem where we already had an analytic expression, but still cool to see done in practice. Okay, now, so I basically introduced the machinery, right? And before we go and apply it to the TFD, I want to take a step back and tell a slightly different story. So I kind of just like gave you this thing to try to minimize, right? So I said, let's just pretend our Hamiltonian is Z, and we now know how we can attempt to minimize the energy of this Hamiltonian. But maybe, right, just maybe, the thing that I really wanted was to prepare the state on the south pole of the Bloch sphere. Okay, and if that was my goal, then if I sat down and thought about it, I could then apply this machinery to, in a fake Hamiltonian of this poly Z operator as a way, as a proxy for achieving this goal. Right, so then this leads to the question, what Hamiltonian or what objective would encapsulate my desire to prepare the Thermofield double? And I should point out, right, like the TFD kind of has this complicated structure. you want it to have the right entanglement pattern, the right phases, the right weights, etc. So it's not a priori obvious what you should try to minimize. However, there was work in 2018 by Cottrell and collaborators that addressed this general question. So, what is the Hamiltonian whose ground state would give you the Thermofield double? The problem, or like the slight technical difficulty there, is that their methods kind of involve Euclidean time evolution, which is hard to do. But luckily, there was also work by Maldacena and Shi that found specifically for the SYK model that the Thermofield double is actually approximately given by the ground state of this, relatively simple Hamiltonian. So what you do is, or what they claim is that if you take the sum of left and right SYK Hamiltonians plus a small interaction term, where the interaction term basically couples twins on both sides. Okay, so the claim is that the ground state of this Hamiltonian approximately gives you the Thermofield double on the original 2 copies of the system. Okay, so like visually, you could think about them as these 2 separate systems where you then connect them with a small wire in between, and then you find the ground state of this, and that would leave you with the Thermofield double on the original 2 copies. Okay, so this is going to be the thing that we're now going to apply our machinery to. And
what actually is the overlap between the ground state of the coupled Hamiltonian and the Thermofield double? Is it actually close to 1, or is it just like exponentially small, but not as exponentially small as you'd expect? Maybe Juan or Xiaolan could answer this better, I don't know. Or Vincent, if you know, obviously.
Yeah, I don't remember off the top of my head what the scaling is. I think in the large n limit, it does go to 1.
So it's exponentially small in n.
Yeah.
Yeah.
And but it's n times a power of mu over k, which is small.
Yeah. Yeah. Okay.
So in some sense, it's sort of classically, if you think of it as a classical geometry, kind of similar, but because it's classical geometry, it's very different. Yeah. That's the thing.
Thanks, Juan.
Yeah. So for the rest of this, I'm going to kind of ignore this approximately and just like treat this TFD Hamiltonian as the thing that we want to minimize. And again, with the goal of putting this on a quantum computer, for now, qubits are kind of like the dominant paradigm. And so to map this to the quantum computer, we're going to use Jordan-Wigner. And under this mapping, the TFD Hamiltonian actually just becomes a sum of polystrings. So we are indeed going to be able to use our gradient techniques for minimizing this. And another thing I should point out that we know about the TFD state is that it should obey this parity symmetry. So in particular, if you measure the left and right energies, they should be the same. If you want to phrase this as a minimization problem, you can actually take the square and say that that should also be 0. Okay, so this is another thing we know should be true about the TFD state. It's not sufficient, but it's necessary. Okay, so the last ingredient that we need is we need some variational circuit now. And before I share what I ended up doing, I want to, again, flip the script a little bit and ask you all to think about it. So what I'm showing here is 2 different variational circuits. Circuit A has RX gates with C naughts in between, and circuit B has Ising and tangling gates, but with RC in between. Okay, so the question, right, is like, which one of these do you think would do better at preparing the Thermofield double? Okay, so, right, the short answer to this, at least from my perspective, is that I have no idea. This kind of goes back to the point I was trying to make earlier, that like circuit design is really hard and very unintuitive. So if you had a strong intuition for which one of these is better, feel free to email me after the talk. Again, I would, I think there's some other knowledge gaps you could probably help me fill. So, barring any a priori reasoning about how to design the circuit, what I want to say is, let's just let the hardware guide us. So in the literature, this is what's known as like hardware efficient circuits. Okay, but what I'm outlining here is basically a skeleton. Okay, and then whatever quantum device you have available, you'll kind of plug in the pieces that you have. Okay, so the skeleton looks like this. On all of the qubits, you're going to apply 1 qubit rotations. Turns out you can, if you have these 3, if this sequence of 3, it generates an arbitrary 1 qubit rotation. And then after that, it's going to be 2 qubit entanglers between neighbors. So here, some of the common 2 qubit gates that people have in their hardware. The line is kind of like maybe the baseline target for connectivity, but if you have a different topology, of course, you could just swap that out. And we're going to consider like D repetitions of this 1 qubit and 2 qubit layer. So D is going to be like the depth. This is another free parameter, so you can just change your ansatz to be larger or smaller with this dial D.
Vincent, just give him a warning. You have like 3 minutes left. So.
Oh, okay.
Yes.
All right, great. So yeah, the one point I want to make is like, this seems like dumb, and it is in a certain sense very dumb, but from a hardware perspective, it's great because you're not, it's kind of agnostic to the hardware, and you're not wasting valuable cycles on trying to compile down to what you have. So just to recap, right, we have our variational ansatz, the thing we're trying to minimize, and a way to minimize it. And the only thing I want to emphasize here is that we're measuring the gradient from the quantum device. And the classical part is like really just a piece of scratch paper that's recording the gradient measurements. Okay, so we're going to repeat this loop many times and see how close we get to the ground state. Okay, so the results. So here I'm comparing to numerics where, it's large enough that I could still fit in my computer. And what I did was I basically exactly diagonalized this Thermofield double Hamiltonian. And the 4 different panels correspond to different realizations of the SYK model. So, you flip your coins 4 times and you get different SYK Hamiltonians. And the main thing that I want to point out is that with about 5 to 10 repetitions of this really dumb circuit, you can, quite easily get to the ground state of these, all these different models. And since I'm running low on time, I'll just say that another thing you can ask is how long does it take to actually run this? What I found was it took about 500 iterations of this gradient repetition. So, if you have a way to automate the runs on your quantum computer, I don't think that's terribly offensive. Okay, maybe I'll skip over this, but the one thing I want to say about this is that in practice, the whole thing relies on expectation values. And there's the thing that I showed here was that if you take into account the fact that these expectation values come from a finite number of measurements, so there's a statistical noise or a shot noise, this is not an obstacle to using this gradient procedure. Okay, so to summarize, right, we used variational circuits to prepare the SYK Thermofield double. It's scalably quantum in that you're not going to be bottlenecked by classical computers. The measurements involved were just these polystrings. So this is, in contrast to measuring something like the entropy of your system, and it's hardware efficient. I think the biggest puzzles left are related to like convergence criteria. So how do we know when we've succeeded with our greedy algorithm? Circuit design is a big question mark for me. Like, how do you design your circuits smarter? And like, how do you even know if the Thermofield double is within your class of states? The other big question mark is quantum gradients. So there's some work that indicates that larger quantum circuits tend to have really flat gradients. So if you're in a situation on the left, anywhere you start, gradient descent will lead you to the bottom. On the right, if you try to do gradient descent, you're not really going to go anywhere because it's flat. And then I think I'll just flash some of the next steps that I think are pretty exciting for follow-up. But yeah, with that, thanks for your time and attention, and I'm happy to take questions.
Thank you, Vincent. We have time probably for like one quick question. So yeah, please.
So I have a quick question. So when you have a Thermofield double with lower temperature, how does your circuit length scale with the temperature?
That's a good question. I haven't looked into that, like the necessary depth. I mean, it's kind of like a, at some level, it would be interesting to do an empirical thing, but it would be nice if there's a more principled way of really teasing out like that question.
I mean, from the complexity point of view, if we take the conjectures like Lenny and Adam et al., then I guess if I understand correctly, the length should go like log beta.
Yeah.
It should grow because the complexity is higher. Yeah, so I think that's the interesting thing. Like, I mean, it should be lower bounded by something like log beta.
Right.
Yeah, so maybe for further questions, we should do in the discussion session. So let's thank Vincent again.